Welcome to the next video in the Measure Theoretic Probability series. This is video 5.2, following up 5.1. Hopefully this was a quick one, just wrapping up the whole point of giving this brief little history, which is to sort of indicate what Vitali showed was impossible and what we're going to try to do about it, and how this kind of all eventually turns into measure theory. So what Vitali really showed is that there is no function which satisfies all of the following properties: that it is a non-negative function, intervals are assigned their length by this function, right? This is our measure function. The function is translation invariant, so if you slide a set of real numbers around, it doesn't change the measure of that set, whether it's an interval or not, just any set of real numbers, right? Because these feathers were not intervals. And yet we still use the principle that whatever their measure is, it would be invariant under translation. And is countably additive. Now, I haven't introduced that word. We'll talk more about it in some future videos, but that's the part where, because the sets of real numbers were disjoint, therefore we could compute its measure by adding up all of the measures of the little disjoint components, right? So because all of those feathers were disjoint, then the measure of their disjoint union is equal to the sum over their individual measures. That's countable additivity. Again, more on that later. And we use the basic principle that every one of those subsets of real numbers was measurable, that the function would assign a measure to them. So we have to, right, if we're going to try to persist in this project of Lebesgue integration and assigning the free images of functions a measure, then we're going to have to give up something here in order to, so that Vitali's impossibility proof does not go through. So what are we going to give up? Well, non-negativity, we just would refuse to give that up because that just too fundamentally violates what we want from the project in the first place, namely that these things should be like the measures of intervals of real numbers. So we couldn't give up non-negativity. We will later on see that we will talk about a thing called signed measures, but they won't be for our current purposes, right? That's a generalization for much later on. We wouldn't want to give up the principle that intervals are assigned their length, because then we wouldn't be getting anything like what we want, because we're trying to capture this notion of the area underneath the curve of a function, right? Its graph. So we won't give up the second bullet point. We won't give up translation invariance, because that, again, just isn't, you might think that, like, I don't know, space is curved and maybe there's, some reason why, like that, why maybe you think that these measures should not be translation invariant, but that shouldn't be baked into the mathematics. We should be able to at least somehow mathematically capture these very flat Euclidean spaces. So we won't give up translation invariant. That leaves two things. Each one we could somewhat more reasonably give up. We could give up countable additivity and say that, well, maybe the problem is this weird infinity stuff. And so finite additivity makes total sense, right? If you have one interval and then a disjoint second interval, and you want to measure their union, that should have measure equal to the sum of their individual measures. But when you do it infinitely many times, maybe something strange happens, and you don't want to say that that's even, like, you just can't even compute that, perhaps. I believe some mathematicians have kind of explored the consequences of that, and there's some interesting results, but it's the less popular thing to talk about in measure theory. So sticking to Lebesgue's solution and what we, usually study when studying measure theory, we're going to investigate abandoning this last option, right? The last principle, which is that every subset of real numbers is measurable. So we will, right, in order to not let Vitaly's proof hold for our theory of measure and integration, we will simply refuse to assign some sets any measure at all. And it will turn out that some of the sets that we refuse to assign measure to are the feathers that we constructed in the impossibility proof. And so when we talk about measuring sets of real numbers, we restrict ourselves only to talking about the measures of the, so to speak, measurable subsets. There will be a distinguished collection of subsets of real numbers, like the intervals, like certain unions of intervals, and so on. Those we will say are measurable, but there are certain collections of subsets of real numbers, like the feathers, which we will not even permit ourselves to talk about their measure. We'll regard that as a nonsense concept.